Friction forces. We've finally made it to friction forces. So what is friction and why does it arise? So if we have something that's along some surface, and we have a box, right? Why is there friction between the surface and the box? Well, if you look at what's going on here, see if I can draw this well enough to represent it. If you zoom way in to this surface, it's not two flat surfaces going on. They're very jagged surfaces, right? So that would be the surface of the box, and this would be maybe the surface of the floor. And so you can see there's parts that catch and cling to each other. If you're trying to push this surface this way across this stationary surface, it's going to grind. And that's what friction forces are. They're microscopic grinding forces. So there's two types of friction forces. Well, there's a few types of friction forces, but the two main ones that we're going to introduce right now are kinetic friction and static friction. So kinetic friction, so one, kinetic friction is, friction force is usually given with this fancy F, similar to frequency. And kinetic friction would be F sub k, like a cursive F sub k. That's when you're actually moving over the surface. So when you're pushing the box, that's like that grinding that I was talking about. So moving over surface or across surface, right? So something is sliding on something else. So if you think of your garage floor and you have a cardboard box and it's filled with something heavy or relatively heavy, you can push it. But when you're sliding across the garage floor, there's some resistance, there's some grinding happening between the box and the garage floor, and that's friction. And it's resisting your push, right? So friction is always in the direction, kinetic friction is always in the direction opposite to motion. So if you're giving it some velocity this way, because you're pushing on it, right, then friction would be acting this way. This is the kinetic friction would be, opposite its motion. So it resists you. The other one that we introduce right now is static friction. Static. And that is also fancy F, but with an S. And that's when the body is at rest on a surface. So at rest on surface. And you say, what? I'm not sliding it. There's no grinding. If it's just sitting there, how could there be some sort of a force? Well, if there's no force being applied and it's actually is just sitting there, then there would be no static friction. But if you have your box, think of a particularly heavy box on your garage floor, right? It has some big mass. So let's say you're pushing it this way, right? So that's the force that you're giving it. But it's not moving yet. You're pushing it, but you're not giving it enough force to move it yet. If you were in space and there were no friction, you would be moving it ever incrementally if it's quite heavy. But the friction, the static friction, is resisting you up until some threshold point. And once you get it past that point, once you're pushing hard enough to actually move the thing, and you overcome this maximum friction force, then it begins moving and sliding, and then you cross over into the realm of kinetic friction. So it's really helpful to keep those two straight, to think of a big heavy box on your garage floor. Push it to get it going. Up until it gets going, it's static friction. And then after you get it moving, then you're into the realm of kinetic friction. So, what are these forces equal to? What can we numerically assign them? How do we include them in our Calculations, Joel. Always the calculations. Well, I will tell you. So, the kinetic friction is equal to a coefficient of kinetic friction times the normal force, N. Yeah? So this is some number that you're either given or maybe you have to solve for, but it's just some unitless number. And then the normal force, right? We're familiar with that. So it's worth remembering this phrase, that U sub k is equal to the coefficient of kinetic friction. That's what it's equal to. That's what we call mu sub k. It's really mu, the Greek letter mu. Okay, so that's kinetic. How about static? Static is similar, but it has its own coefficient. And there's something else tricky. So static friction is equal to mu sub s, coefficient of static friction, times the normal force. But it's not actually equal to, it's less than or equal to. Now, if you've had your coffee today and you're nice and alert, go ahead and pause the video and think about why this would be less than or equal to and not just equal to. If it's early in the morning and you've not had your coffee yet, and you just want me to tell you, then I guess you can do that too. You are in control. So why the less than or equal to? Well, as you push this box that we were talking about, right? As you push this box, I mentioned that there's some threshold force that overcomes its static friction, right? So this would be the static friction. So if you push a little bit, right? If you, we'll leave this. If this is a little push and it doesn't go anywhere because it's not enough to actually move it, this coefficient, the static friction force is equal to, it matches your push force. But if you push a little bit harder, let's just say this hard, and that happens to be the threshold just before, right? So if you pushed with just 0.00001 more newtons, then the box would start moving, right? Or less than that even, right? So just that exact threshold, the maximum that you could push with the box not moving, then that is when it's equal to. That's when you get the equal to part. But before that, when you're pushing less than that, the static friction force is just matching your push. If you pushed with a small force, right, less than the threshold force to get it going, the static friction, in other words, if it worked for equals n, if this equation, if the universe worked in such a way that this was not less than or equal to, but just equal to, then this would match, this would be some great force that way, and you'd push this way, and the box would go that way. That doesn't make any sense, right? So it matches you, it resists your push up until you get past this threshold point, and that is the maximum static friction force. And then once you go beyond that, you've gotten the box moving, right? Now the box has some velocity, and so now it's sliding and grinding along the surface, and we're in the realm of kinetic friction. So this problem that we're going to do gets those two scenarios straight because it has you do just what we kind of described. You're pulling, it so happens, you're pulling a box until it overcomes coefficient of static friction, and then you continue pulling it, and we find the kinetic friction. So here's the problem we're going to do here. bigger. How's that look for you? Okay. So this is the problem we're doing. So you want to move a 500 Newton crate across a level floor. To start the crate moving, you have to pull with a 230 Newton horizontal force. So that in order to get it moving, you have to pull 230 Newtons. So that would be like the maximum static friction force, right? Once the crate breaks loose and starts to move, you can keep it moving at constant velocity with only 200 Newtons of force. What are the coefficients of static and kinetic friction? So we're going to go through our process again. Just start in this color. So one, what are we trying to solve for? We're trying to find u sub s, and well, here we'll do equals what? And we're trying to find mu sub k equals what? Mu. Okay, so sketch the problem. It is pretty simple, so you might be able to skip this, but I'll do it anyway. I'll try to go fast. So we have this surface here, and you have this box here. And does it give you any mass or weight? No, it does not. Oh, yes, 500 Newton crate. So what that means is that the weight is equal to 500 Newtons. Yeah. All right. Does it give you anything else? Nope. Do you need anything else? Nope. I mean, there's a push going on. There's a pull, right? So I guess there's some tension force that's going to happen. All right. And there's friction here. So you could do mu sub s and mu sub k if you want to remind yourself to include friction. You'll develop your own system that works best for you. Switch to a new color. And we'll do 3 and do a free body diagram. So there's only one body involved. Of course, there's this other stick man, but we don't care about him. He's just the one exerting the force, and he's exerting a horizontal force. And so we don't care about his body. But there is 2 scenarios happening. First, he's pulling and the box isn't moving, and then he's pulling and the box is moving. So this may not have been obvious upon reading the problem, but I'll tell you since we're doing it together, and this is what examples are for, it's helpful to do free body diagram for the before the box breaks loose, and then another one for after, because the forces are different, right? Forces are different. Before, he's exerting 230 Newton horizontal force, and then after he's only exerting a 200 Newton horizontal force. So it's 2 different scenarios. So for this one, we have its weight, mg, or you can say W because that's how they gave it to us. So we'll do that. Weight, it has a normal force. It has this horizontal pull force and is probably greater than its weight. And so this is going to say F. That's just F. How about that? It's just the force that we're pulling it with. You could say T because it's on a cord. Let's do T. That's the tension force. Because he's using a cord, I guess, to pull it. All right. And then, if this were last video, we'd be done. But now we have another force resisting the pull, right? So we have this F sub S. So friction, static friction. And it's going to be, I kind of misdrew that, it's going to be the same as the tension if it's not going anywhere. It is about the same length. It's going to be the same length as the tension pulling on it. There we go. Because it's not going anywhere. So we'll say A equals 0, right? A equals 0. How about that? It's not going anywhere in the before. But after, then we have something different. So we still have the weight. We still have the normal. We still have the pull, but it's less. So actually we'll do T1 here, fine. T1, and T2. Or you could do T before and T after. How about that? T after. Well, that kind of looks like A and B, which would go the other way. Well, do whatever you want. T2, T1, just as long as you're consistent with your drawing. And now we have a friction force, but it's kinetic friction. Kinetic friction. And this time there is a net force, so I drew this one smaller. And so now there is a net acceleration, and it's going to be that way. Okay. So we've just added new forces to have to deal with, that's all, right? So now we do our part 4. Let's go over to here, do pink again. 4, get our equations. So before, we have sum of the forces in the x is equal to T1 minus F sub s, and that's equal to 0 because it's not moving. Sum of the forces in the y is equal to n minus w, and that's also equal to 0. It's not crashing through the floor. Maybe we need both, maybe we don't. It's easy enough just to write it. Here's the after scenario. They're nice because they're all along our axes, right? So we don't have to find component vectors of anything. Fx for the after scenario is T2 minus kinetic friction. And that's equal to some acceleration, because now this is after we've got it going. And the sum of the forces in the y is equal to the same thing, n minus weight, and that's 0 because it's not going through the floor or flying off the ground. So there's our equations. And let's see if that's enough. So we have, what do we want to find first? We want to find mu sub s and mu sub k, right? And where do those come from? Remember? And then, well, here, I'll say max, right? So the maximum at the point that it breaks loose. And then mu sub k times n, right? So we have f sub s and f sub k as part of our equations, so we should be able to find this mu of each, kinetic and static. So we should be in good shape here. So I say we can safely move on to step 5, where we solve things. So f sub s is just mu sub s is equal to, and we're doing it at the maximum, right? So in the problem, to start the crate moving, you have to pull with 230 newtons of force. If it said you pull with 150 newtons of force and it goes nowhere, then we would not be able to say static friction maximum is 150 newtons. But we know that the static friction maximum is 230 because that is what gets it going. So that is the maximum that breaks it loose. And so remember that it was less than or equal to, the static friction is less than or equal to mu sub s times the normal force. Well, now this is the equal to part of it because it's at that maximum, right, when it breaks it loose, that threshold maximum. So mu sub s times the normal is equal to T1, right? T1. And we can solve for the, we have T1 and we can solve for the normal, right? So this means, I'll do it right in here, the normal force is equal to the weight. So they gave us the weight. It was 500 newtons, right? So that would mean that mu sub s times the weight is equal to T1, or that mu sub s is equal to T1 over the weight. Okay, So, and we know that, and we know that, so we've solved for mu sub s. You can plug in the numbers and find it. I'll let you do that. How about the other one? So in our other scenario, to find the coefficient of static friction, we have mu sub k. So I'm just taking the sum of the forces in the x here. I'm just expressing this in terms of what it actually is, which is mu sub k times n, is equal to m a, let's see, is equal to T2 minus MA. All right. So we have T2, it tells us that. We have the mass, right? Oh, I said it was equal to MA, but when it starts to move, you can keep it moving at constant velocity. So I made the mistake of thinking we were in Newton's second law realm, where it has an acceleration, but it does not have an acceleration. It's constant velocity, which means acceleration is 0. So that should have been 0. And so now that simplifies things here. So we have mu sub k times n is equal to T2. So we also, again, have that. And again, the normal force has not changed, right? So that's mu sub k is equal to T2 over the weight. And you can compute that if you want. I'll write out the answers here. 0.46 is mu sub s. 0.46 is a unitless number because, remember, you're dividing newtons by newtons here. And then mu sub k, if you calculate that, is equal to, what did I get there? 0.4, my notes got very far away. 0.40. 0.40. All right. So you might need to have a before and after scenario if you're dealing with both. And hopefully that illustrated how both of those come into play. So let's do another example here. So this one is one that I love. It's kind of a quintessential Newton's laws problem. We can finally do it because we know about friction now. So here we go. This is a more difficult problem, so you can't accuse me of only doing easy problems, huh? Let's see how that looks for you. See that blue CP up there? That means, in the textbook I'm working on, means challenge problem. Way too big. Challenge problem. So I'm walking you through a harder one. See, I know we don't see the CP because it's off our screen. Alright. We'll give it that much effort and call it quits, huh? You could see that. Alright. So we have this scenario here. We have a mass connected to a cord that goes over a pulley that's being pulled up a ramp, and there's a weight on the other end of the cord falling down. Yeah? So we have M1 given, we have the angle given, the coefficient of kinetic friction between the block and the incline, mu sub k, is given. What must be the mass of M2 of the hanging block if it is to be if it is to descend 12 meters in the first 3 seconds after the system is released from rest? So immediately, given this kind of information here, time and meters and stuff, we know we're going to use some of our kinematic equations, right? So we should already have that in mind, that we're going to need to pull some kinematic equations to find out what's going on. So if you want, go ahead and pause this and see if you can solve this. All we've introduced is friction, and it gives us mu sub k, and so we're only dealing with kinetic friction. So if you want, go ahead and see how far you get, and then you can come back and have this video portion kind of walk you through what you missed if you missed it, or celebrate that you got it right. So, first off, let me go to a new color. First off, what are we solving for? So 1, what are we solving for? What must be the mass of M2? So M2, all of this is wondering what the mass of M2 must be, right? It gives us some other information we'll label. So 2, we can make a simplified diagram. I won't make a simplified diagram because this is as simple as it gets. So I'm going to just pull this down here and talk through this diagram. We'll call this 2, right? So we have alpha, that's equal to 53.1 degrees. We have M1, which is 20 kilograms. This is what we're searching for. We have kinetic friction, mu sub k, the coefficient of kinetic friction equal to 0.40. It's a unitless number, remember? And so what is the kinematic portion of this question? We want this block to descend 12 meters in the first 3 seconds. All right, so let's say wherever it is right now, we're going to call that y naught. Why not call that y naught? So I'm just saying this is the vertical direction, right? Positive y direction, I mean, is going to be down because that's the direction it's going. And so we want it to descend some amount y. And so from y naught to y, if y naught is 0, y naught defined as 0, then y is going to be 12 meters. You can say this is the positive y direction if you want, but that would make your 12 meters negative, and you'd have to keep track of that. You absolutely could. I'm just going to say this is the positive y direction, so that means that our y, which means the y position, as we've defined it, at time equals 3 seconds, is a positive 12 meters. All right, so that means that there's going to be some acceleration this way, right? There's some acceleration we have to keep track of. And time is equal to 3 seconds. So just to catalog everything that it's kind of given us at this point. We've written all our stuff out. I don't think there's anything else that it was given us. Oh, well, it's given us the velocity at, we'll do v naught y, right? The velocity, 0 meters per second, because in the problem it says, can you see all the problem still? It says, after the system is released from rest. So that means the initial velocity is 0. So that's the kinematic information we have. Let me see if everything's on the screen. Yes. Yes, okay. All right. So this might be the tricky part, you might think, right? But we've dealt with kinematic stuff before. That's why we slowly build up. So it's kind of like going back and doing things you're already comfortable with. So let's do next our free body diagrams. I'm going to switch to a color that's easier to see, I think. Okay, so that was 2. So 3 free body diagrams. We have 2 bodies. They're both moving. We expect that they will both be relevant. We're given information about both. So let's do first for M1. M1 would be the block on the ramp. So it has some weight, m1g. There's 2 masses, so you can't just say mg. You have to specify which m you're talking about. It has a normal force, which is something like this, normal force, right? It has a tension force. It's being pulled this way, tension. And we don't have to write T1 and T2 because whatever the tension force is on M1, that's the same as the tension force on M2. The pulley just redirects that force. And now we have this kinetic friction. So, kinetic. Fancy F sub K. Okay. Anything else happening? Are there any other forces going on? I don't think so. So how should we choose our axes? Right? So we have some acceleration that's going to happen, right? The mass m2 is going to accelerate downwards, and the mass m1 is going to accelerate this way too. So we have an acceleration that's this way, right? So that's encouraging us to make our axes this way. And also, if we do that, we have 3 of our vectors in line with our axes. So I'm going to go ahead and say that's enough convincing for me. Let's do our axes like this. So that way only this one is weird. Only this one needs to be found in component form. Okay. So mg, we'll just do, I don't know. mg, so we have the component of its weight, m1g, that is in the negative y direction, and we have the component of its weight that's in the negative x direction, and that's going to be something else. And so we can figure that out. So what is our angle? This is like our ramp, and that angle is alpha, right? So think about what the angle might be. What is the angle? Well, if this is a 90-degree angle, then this here must be 90 minus alpha. And if this is a 90-degree angle, then this must be alpha again. Right? So this is alpha there. And I'll go ahead and erase this as well. That's all we need. That's alpha. So then this must be, it's the one adjacent to it, and this is the hypotenuse. So this must be m1g cosine alpha. And this must be m1g sine alpha. One is cosine, the other one's sine, right? Because they're 90-degree angles, they're different components. All right, so that's for m1. Now let's do for m2. Oops. m2. So free body diagram for m2. So this is one that's hanging, and it's also the one that we're concerned with. So it has some weight, so m2g. Now that I gave this a vector here. There we go. And this is also a vector. There we go. And it has tension this way, tension, and that's the same t as before, right? It's just redirected. It has some acceleration, I'll do this, it has some acceleration this way. If we wanted to label that, it might help. But that's all the forces that I see. So how should we choose our axes? Well, the x doesn't really matter. There's nothing in the x if we define it this way, which seems obvious, and just like we defined it before, we'll be consistent with that. See how we defined this as the y, positive y? We'll be consistent with that. So this will be the y. How about that? Seems fair to me. And so, because of that, the acceleration is going to be completely in the y for this scenario, and completely in the x for that scenario, right? Here, I'll do it in pink. I usually do acceleration in pink. It's going to be this way. All right. So now, let's find our equations. So, I'll use this color. It was a nice one. I wasn't done with it. 4. Find our equations. So sum of the forces in the x is equal to t minus f sub k, and there is an acceleration in that direction. So, one more force involved, the component of the weight. So minus also m1g and that's equal to m1a, the acceleration of m1. And since they're connected, right, the acceleration of one is going to equal the acceleration of the other. Right? So whatever m1 is accelerating up the ramp, whatever rate of acceleration, m2 is going to be accelerating down, or in the positive y direction as we've defined it. So that's some of the forces in the x, some of the forces in the y, looks like this. We have n minus the component of the weights, m1g cosine alpha. And there's no acceleration in the x. It's not crashing through the ramp or flying up off the ramp. All right, coming over here, sum of the forces in the x is equal to nothing. Sum of the forces in the y is equal to t, oops, a little high there, t minus m2g. And it is accelerating in the positive y direction, so m2a. All right, so there's some equations. If you weren't sure that we needed kinematic equations, then you could proceed from there. If you were thinking that maybe it's a red herring that they gave you all that other information, you could proceed and you'll find out that you don't quite get there. And so we need more equations. We need kinematic equations. So what kinematic equations do we need? What are we trying to solve for? What are we needing? Well, we're trying to solve for m2 given some acceleration. So we're trying to solve for m2, right? Something. m2 is equal to something. We got some m2 over here, but we don't have enough to solve it. And we need something for a. So we can use kinematic equations and some of these initial, or not initial necessarily, but some of these pieces of information here to find what exactly a is. So the values that we're given, we have v naught, we have y naught, we have y, and we have t. Yeah? So what kinematic equation works then? I'll give you a sec, and we're trying to find a, right? So go ahead and look for yourself and see if you can find which kinematic equation you think works best to solve for a. These are the values we have, and we're trying to find a. You should have them in front of you when you're doing these problems, or at some point you might memorize them. So the one that I see is what we had previously labeled constant acceleration equation 2, which goes like this. And we wrote it probably in terms of x, but I'll write it in terms of y since that's what we're working with here. Y equals 1/2 a t squared plus v naught. And that's in the y direction. You don't have to include that if you don't want. T, it's just being explicit, plus y naught. Right? Just like you don't have to include this because it's the same. But we'll do it anyhow. Okay, so before we solve for a, right, because we could solve symbolically for a for all of this, you can do that. But before we do that, it strikes me that some of this might cancel out, right? So v naught y is the initial velocity that mass m2 has, the mass that's hanging off of the thing, this mass over here, right, that's connected. So did it have any initial velocity? No, it was released from rest. So v naught y is 0. So we don't have that. And then the way that we defined it, y naught, this was y naught, and this is y, right? So we called y naught 0 so that we can call y 12, right? So y naught is 0. Does it seem like we've cheated here by calling y naught 0 so that way we can cancel it out? We're not making up numbers. We could have called y naught for no reason. We could have called it 5 meters. But that would have made y 5 plus 12, so 17 meters. We could have done that. But do you see how it's kind of nice to define y naught 0 when you can? Because now, if we call that 0, and this 12 then, 12 meters, it descends 12 meters, then we can say, well, y naught is 0. And so something cancels out. So you're just trying to find ways that make your life easy. And at first it might be hard to recognize them, but the more problems you do, the more comfortable you get and the more these opportunities jump out at you. So what we're left with is, hopefully that's not too small and you can see everything, what we're left with is just this part. Y is equal to, well here, I'll just solve for A right in the same step. A is equal to 2y over t squared. We're not done yet, right? We're not done yet, but this gets us a nice piece of information because we have y, right? Y was that 12 meters and t was the time, right? Which was, I believe it was 3 seconds, whatever it was. It's listed up there. So now we have A, but what we're searching for is M2. So coming back to our equations here, we're searching for M2, right? So we have M2 over here. So how are we going to do this? So we can plug in stuff for A, right? But we have this T involved as well. We have T. How do we get rid of this T? We're in the next phase of the problem. So I'll go back and change the color here. Gold. Home stretch. So we have this T. We got to get rid of T. But we have an expression over here that involves T as well. We're given the mu sub k. We have m1. We can find the normal force, right? Because we have m1. We have g. So this might be coming together for us. So if we solve this equation up here for t, right? So let's rewrite this whole equation. So t is equal to be explicit, t is equal to m1a minus mu sub k times n, right? And we'll write that all out because we know we'll need to eventually, minus m1g. So there's t. Now we're going to take that, we're going to plug it in there. And so we have m1a minus m2g. Oops. Let's write the whole thing out, huh, Joel? Mu sub k n minus m1g minus m2g is equal to m2a. Do you see what we've done? We just solved this one for t. We got that, and then we plugged it in here, and now we have this big long expression. Okay. So now, is there a way that we could solve for m2? Well, yes, we can. m2, let's see, a minus g is equal to m1a minus mu sub k n minus m1g. Did I do that right? Did I do that right? Let's see. A plus g here. If we move that over. And then m1a. Let's see. I can't find where I did it wrong, but I see my notes do something different, so maybe my notes are wrong. M2. I get something wrong when I plugged stuff in. minus m2g. M1g minus m2g. Alright. I can't find what I did wrong, but I may not have made a mistake like before. I thought I did something wrong. So m2 is equal to m1a minus mu sub k n minus m1g all over a plus g. Boy, it just feels like I did something wrong. I think it should be g minus a on the bottom there. Check it. Check it for me. Find where I made my mistake. It's just algebra, but my brain, it's about 100 degrees in here, and my brain is frying, I guess. And then also we have a, right? We solved for a. A was equal to 2y over t squared, so that's equal to m1 2y over t squared minus mu sub k times n. What is n? You could find n. N is equal to mg cosine of alpha, right? So mu sub k mg cosine of alpha minus m1g. All that is equal to, or over a plus g, although I feel that it is not for some reason. And we're plugging in our a's here, so 2y over t squared. And if you plug all that in and your equation is right, we should get 36 kilograms. All right, so there you can test to see if I did something wrong, because if all that doesn't compute to 36 kilograms, then I did it wrong. Somewhere in there I made a mistake. You're probably screaming at the screen. Just move on, because we already get where you made a mistake. So I will. Okay, so that is a quintessential problem that I wish would have ended a little bit more gloriously than it did, but what can you do? All right, so there's just 2 seconds before we end this video. There's 2 other types of friction that might come up, but are worth mentioning nonetheless. So rolling friction and fluid friction. So we'll talk more about fluid mechanics in lecture 12 if we get there, if we get that far. But read about both of these additional friction types in your textbook. So rolling friction is just the friction of something that's rolling along a surface, right? So it's rolling, and it's a different kind of friction. So mu sub r. And fluid resistance, which is often called drag force, right? So air is a fluid, right? And so that is just this big cursive F with no designation subscript, and at small speeds it's proportional to your speed, and at large speeds it's proportional to the square of your speed. So that's like when you're driving the car, the faster you go, the more drag force there is, and the more resistance, right, therefore, of you pushing through the air, and so the lower efficiency your miles per gallon gets. So read about those. We'll come across fluid mechanics later. All right, that's it. Next, we go real quick through circular motion. We'll do one quick example, and then we're done.